Vineyards in the Cosmos, excuse me. In the 1920s, Austrian Rudolf Steiner preached moon-centric science. This approach to farming is described as spiritual, ethical, ecological. Referred to as biodynamic farming, this method came about when farmers turned to chemicals to control poor soil conditions, pest infestation, and a variety of maladies plaguing their vineyards, crops, and gardens. Biodynamic farmers go beyond organics. The basis is the use of non-chemicals and strive to grow in tune with the cosmos. They achieve this by coordinating their soil treatments with the lunar calendar. Let's look at the lunar calendar. It categorizes days into 4 groups: flower, fruit, leaf, and root, based on where the moon is within the various constellations that you can see there on that diagram in the middle. Examples: fruit days occur when the moon is in any of the fire signs. Radishes would be harvested on root days because radishes are a root. One of the most interesting elements of biodynamics is the beliefs go beyond the field and right into your wine glass, thanks once again to the moon. The above image is from a paid app which provides you with a 24/7 year-round calendar. This calendar is helpful in recommending good, bad days to drink, uncork, etc. As you can see there, time of day and day of the week. Like a religion, there are degrees of devotion to these methods. Some vintners refuse to open wine on root days, while others organize tastings around the lunar calendar. A long-term study was done at a winery in Ukiah, California. They grew 2 blocks of grapevines, one biodynamically and one organically. We found no different grape qualities or cluster and berry weights. However, the participants in the blind taste study of said bottled wines picked the biodynamic farmed wine over the organic farmed wine in regards to taste. They reported a stronger, clearer, more vibrant taste. In closing, for every biodynamic farmer, there are a half dozen or so who remain unwilling to decipher the interstellar impact and proclivity. And to those I say, cheers, the end.
Well, thank you, Kent, and thank you, Moon, for doing that. I'm going to go ahead and get our main speaker queued up here. It is my pleasure to introduce our main speaker, Patty Bolan, of UC Davis. Patty is a third-year grad student in the Department of Physics and Astronomy at UC Davis. She's currently analyzing data from some of the first galaxies formed within 1 billion years of the Big Bang, but has a diverse background in other astronomical topics. Patty Bolan, the solar corona. He stopped sharing so she can start sharing.
I'm getting the same message that my video can't be started. I don't know if it has to be, but oh, okay, got it now. Yeah, okay, there it is.
There you are.
Yay. And then let me share screen.
Please pay no attention to the man behind the curtain.
Exactly. All right. Cool. Let me switch that. All right. Cool. So you can all hear me and everything?
Yes, can hear you just fine.
Yay. Okay. Awesome. Cool. So as Steve said, thank you for the introduction. My name is Patty Bolan. So I'm a third year now, just starting my third year at UC Davis. We just officially changed the department name to Physics and Astronomy, which is exciting, instead of just physics. So my research now, actually for my PhD, I'm working on basically the first galaxies that ever formed, pretty much the furthest away light that we can see with any telescope on Earth. But before that, I did my undergraduate degree at Boston College. And while I was there, I did my thesis at the Harvard-Smithsonian Center for Astrophysics. And I worked in the solar group there. So rather than the furthest away light, we can get basically the closest light from the closest star that we have to us. So kind of a big change, but I'm still really excited about solar research. And then after I did my thesis, I did a 6-month internship there. So worked a little bit more on looking at the solar corona. So I'm going to be talking about basically focusing on the solar corona, which I'll get into more detail later in the talk, but it's basically the atmosphere of the sun, or the outer layer. There's a lot to talk about in the sun. It's a really cool thing to study because it has huge effects on the Earth, obviously, so we'll talk about some of those. And it's also the easiest case study of a star that we can look at. It's the one that we can study in the most detail. So it gives us insight into stellar structure, evolution, and formation, as well as kind of allowing us to figure out what's happening with space weather and how these things affect the Earth and our atmosphere. All right, so okay, cool. So first we can talk about what a star actually is. So our Milky Way alone has 100 to 1,000 billion stars as an estimate. This is a picture of a Milky Way. And so that's just our one galaxy. And in the universe, there are estimates that there are that many number of galaxies, 100 to 1,000 million billion galaxies. So you can only imagine how many stars there are, trillions upon trillions. So this is the closest one to us. So it actually gives us insight into what could be happening in all these other trillions and trillions of stars that are out there. So a couple things define a star. The first one is it's a dense ball of gravitationally bound gas. Basically, you have tons of gas kind of just milling about the galaxy. And at some point, the gas particles will gravitationally bind themselves to each other. They'll get closer and closer. And then once they get close enough, they get really, really dense. And as matter gets denser and falls in towards each other, it heats up. So the other key element of a star is that it sustains nuclear fusion inside of the core. So this is what distinguishes it from a gas giant, like say Jupiter and Neptune, because those are also defined as dense balls of gravitationally bound gas. But the difference with stars is that you have a lot more matter in a smaller space in the stellar core, and that will sustain nuclear fusion. So what's happening in these stars is you have hydrogen atoms. So that's just defined by one proton, usually one electron. And the fusion that's happening is you have 4 of those hydrogen atoms fusing into one helium nucleus. So that's pretty much how we're going to define a star, is it's just a ball of gravitationally bound gas. And it's hot enough, dense enough that it gets to high enough temperatures that it can fuse hydrogen to helium in its core. So let's look at the sun in its solar cycle and see how it compares to all these other stars that we've been able to study both in our Milky Way and beyond. So this is the stellar evolution. This is pretty much what every star goes through. There's slight variations based on the masses of stars. So the sun is actually a pretty average star. When we talk about stars and actually galaxies and most astronomical objects, defining their masses, we usually scale it by solar masses. So this sequence that I'm showing here pretty much happens for stars that are about 0.8 solar masses up to about 8 solar masses. There are stars that are smaller than that and ones that are larger than that, and they'll go through slightly different life cycles. But so from the data we have, the average size stars, which is what we define our sun as, will go through this sequence. So if you start over on the right side at the T Tauri sequence, that's pretty much what's called a protostar. So this is where you have that gas, remember, that's gravitationally binding itself together, and it's kind of all clumping together and becoming spherical and clumping in towards a certain thing. And then once it starts that fusion in the core, hydrogen to helium, that's when it hits the main sequence. So right now our sun is on the main sequence. It's about halfway through its lifetime. So our sun is 4.5 billion years old, and we estimate it'll die or go into the red giant phase at around 10 billion years old. So the main sequence is defined as any star that has that hydrogen to helium nuclear fusion in its core. And the amount of time the star spends on the main sequence depends on its mass, basically. So if it's a bigger star, it'll burn through that hydrogen fuel a lot faster, and it'll have a much shorter lifetime. Really small stars have really, really long lifetimes, just because of how they scale by mass. So right now, since the universe is about 13.8 billion years old, stars that are less than half of a solar mass, we say pretty much will last forever or have infinity lifetimes, just because they'll last so much longer than the age of the universe right now. And we're not sure what they do at the end of their main sequence lifetime. And then these next branches after it, subgiant, giant, and asymptotic giant branch. We're not going to go into too much detail about that, but what happens there is that's when the core runs out of hydrogen. So it's fused it all into helium. That core will collapse. And after that collapse, you'll have a big shell that comes out on the outside. And that outer shell will then sustain hydrogen to helium fusion, while the core, as it gets denser and hotter, will fuse that helium into heavier elements like carbon and oxygen. All right. So going past those giant branch sequences, the next thing that happens is the planetary nebula sequence. It actually has nothing to do with planets. That's just historical naming, because they thought it looked kind of like planets when they first saw them with the naked eye. But what happens there is that outer shell on the outside eventually will get expelled outwards, and it releases a ton of gas, and that gas gets ionized by photons that are dancing around from the core. And when you have ionized gas, that's when you get these really pretty, like, rainbow nebular looking clouds that people like to look at. So things like Cat's Eye Nebula, Helix Nebula, Orion Nebula are all really popular ones. That's just basically big clouds of ionized gas. Sometimes they're also called nurseries for stars, because after you've expelled out this gas, that gas can clump together and start the life cycle again and form a new star out of that. And then what's left after the planetary nebula is the white dwarf, which is basically just a small inert core. It's no longer fusing, and it's usually just made of carbon and oxygen. And basically that white dwarf will last forever. They're very small, very faint. Usually it's about the mass of a sun stuffed into the radius or volume of the Earth. So they're just really dense, heavier elements that have already fused from helium. And it's basically what's left over. And those, we kind of also say that they last forever. Eventually, it's been theorized that because white dwarfs really slowly cool down over their lifetimes, they'll eventually turn into black dwarfs. But due to the age of the universe, none of those exist yet, because it would take longer than 14 billion years for that to ever happen, even from the first stars. All right. So now we can talk about the sun. So we said it's a main sequence sun, 4.5 billion years old, about halfway through its lifetime. And since this guy is really close to us, or it's about 92 million miles away, but that's the closest we have, we can get a lot of insight into its structure based on spectroscopy and imaging that we can get of the sun. So we have here the core, right? That's what we said on the inside, which is taking hydrogen and fusing it into helium, because it's a main sequence star. On top of that, we have the radiative layer. So what that is it's just pushing photons out from the core and expanding them outwards. So this is what's called the stars in hydrostatic equilibrium. which means that it'll actually roughly stay the same radius as long as it's on the main sequence and still has hydrogen to fuse. And it's a perfect balance between pressure, outward pressure due to the thermonuclear fusion, and inward pull due to gravity. So they kind of balance each other out. And if one dominates, then it's kind of like a thermostat where it'll regulate itself. So main sequence stars pretty much stay the same luminosity and size for most of their main sequence lifetime, which is pretty cool. So as photons are radiated outwards in the radiative layer, and then next we have the photosphere. So the photosphere is what we see when we see the sun. It's the thickest layer and it's the brightest layer. It peaks in the optical wavelength with yellow light, so that's why it appears yellow to us. So pretty much when we talk about the sun, we usually say it's 5,800 Kelvin, and that's the temperature of the photosphere, because that's what we can most directly measure. All right, and then the next layers are kind of all defined together as the outer layers of the star. The photosphere we usually count as the surface, but the chromosphere is basically a reddish thin layer on top of it. This is where, when we talk about magnetic field lines in a little bit, some of them, a lot of them are going to be rooted in the chromosphere, but this is a very thin layer, so we can't see it because it's outshined by the photosphere. And outside of that is the part that I'm most interested in, the corona. So like I said, this is usually called the atmosphere of the star. It's really, really hot plasma. And one of the most interesting things about the corona is that it's 1,000,000 degrees Kelvin, way, way, way hotter than the photosphere. And it's still kind of a mystery as to how it gets that hot. And some solar probes out right now are kind of trying to solve that problem of how does the corona get this much hotter than the photosphere. It's also the biggest layer. It expands really far out from the sun. It takes up about half of its, or more than half of its total radius, right? And we'll talk a lot more in detail about the corona later. And then the solar wind, this last one, it basically just is what it sounds like. It blows out matter, it blows out photons and plasma from the sun in these events that we'll talk about, like flares and coronal mass ejections. It's what guides space weather. So space weather is just weather that happens outside of the Earth's atmosphere, and it's pretty much dictated by the sun. So any particles and photons, radiation that get blown out by the solar wind, that's what affects space weather. All right. So before we actually get into the corona, I want to motivate why we actually study the corona. And it's actually very relevant for anyone on Earth, whether you're into astronomy or not. But the main thing that you might hear about a lot in the news and stuff like that is coronal mass ejections. So this is basically just a huge burst of plasma and matter that comes out from the corona of the sun. So they can interact with Earth's magnetic field. So we can talk about this diagram. Basically, the Earth, because it has a molten iron core, has its own magnetic field. These blue lines here are magnetic field lines. That's just pretty much the lines that a charged particle will follow. They follow the magnetic field lines, and they always point from the south to the North Pole. And it has its own magnetosphere. That's basically where magnetic fields dominate over any other force. So that's what's happening. It's outside the Earth's atmosphere. It has this big magnetosphere. And this thing actually protects us usually from the solar wind. So they're usually, any charged particles or matter will be deflected by a magnetosphere because it's so strong. So what you're seeing here is the solar wind comes out. Magnetopause here is basically just the boundary between the magnetosphere and where the sun's magnetic field dominates. So usually they'll get deflected by the Earth's magnetosphere, and we're safe from things like that. But there have been instances of huge giant coronal mass ejections, usually when the sun's at solar maximum, which we will get to later. And they can cause damage to anything that has to do with communications or electricity and magnetism. So we have hundreds and hundreds of satellites, right, floating around in our atmosphere. So if we have a strong enough CME, or coronal mass ejection, that our magnetosphere can't deflect it, then that radiation from the CME and the flares associated with it can really mess up satellites and basically cause giant communication system errors and failures, right? So one of these actually happened, a really bad geomagnetic storm caused by CME back in 1859. So this is the largest ever recorded geomagnetic storm. It was huge. Luckily, the highest form of technology then was a telegraph system. It did knock the whole telegraph system out of use for, I think it was a few days at least, until they got that all back together, but it basically destroyed and fried all of that for a while. But now, if we had something like that happen, it would cause pretty much worldwide blackouts. All the satellites that would be hit would be down. It would be a lot bigger of a problem. I've seen estimates that would be like $6 to $10 trillion to fix an event of this scale. If something like the Carrington event happened today, it basically would be a huge global disaster. This picture here is what it would look like to have the aurora borealis over New York in an event such as this. And the one in 1859, they saw the aurora borealis almost all the way down to the equator. It was seen in Mexico, Northern Australia, and Queensland, and then down in Colombia in the Southern Hemisphere. So, because basically the aurora borealis is also caused by space weather. This is when solar wind sneaks past the magnetosphere, not necessarily a CME or a super strong geomagnetic storm, but the radiation and particles from the solar wind will get into the magnetosphere and they'll ionize photons inside of Earth's upper atmosphere. And when these photons are ionized, it's actually just like the planetary nebulae that we talked about before. They'll light up and turn all these different colors. Usually green because of the gases and elements that we have in our atmosphere. That happens to be the color of the wavelength of light that comes out when these photons are ionizing. All right. Another event that recently happened is we had a huge coronal mass ejection in 2012 on the same level as the Carrington event. This is a video image of it because now we have solar telescopes that capture all these things in real time. So in 2012, this giant CME blast of plasma coming out of the sun just missed the Earth by 9 days. We just rotated past it 9 days ago. So because of these things happening, and we know that the damage that would be done because of them, a big effort in solar physics right now is being able to predict coronal mass ejections. And to do that, we need to better understand the corona of the Earth and what's happening dynamically with the magnetic field lines, because it's mostly magnetic events and complicated magnetic field lines that cause all these things. All right. So now let's actually get into what is the solar corona and why does it cause events like this to happen? So like we said, it's the outer layer of the sun. You can only see it with the naked eye during a total solar eclipse. So if any of you saw the 2017 one, the total eclipse that went through the US, these white bands out here that you would have seen when the moon went in front, that's the corona. In any other circumstance, when you look at the sun, all you see is the photosphere because it's the brightest part. But during a total eclipse, the moon perfectly blocks out everything out to the photosphere and you can actually see the corona because then it becomes the brightest thing coming out of the sun. All right, so like we said before, extremely high temps, that's still kind of a mystery. The corona is at 1,000,000 degrees. There's really turbulent magnetic field activity happening. So that's kind of the bulk of what we're going to be talking about. And there's nothing on Earth that produces this much energy or this many complicated magnetic fields. So the sun is pretty much the only place we have to study turbulent activity like this. It's kind of our laboratory for stuff like that. So events that happen in the corona that we're going to look at, CMEs that we talked about, solar flares, and sunspots. So we're going to define these on the next slide. All right. So this is an X-ray image of the sun. We usually look at images of the sun in an X-ray filter because things in the corona shine brightest in X-ray and UV light, which is a little bit higher frequency and energy than optical light. So usually when you look at the sun, you see the photosphere that peaks in the optical range in yellow. But when we want to look at the corona, we usually use X-ray telescopes because that gives us more information on what's happening in the corona. All right, so the first thing that we can see here is a solar flare. A solar flare is pretty much just a burst of photons that usually comes on all frequencies, but like I said, these things will peak in the UV and the X-ray. So they look like really bright against everything else across the solar surface because they're just bright flares. These happen, the way I like to think of it is you have these really twisted magnetic field lines kind of going everywhere. And we'll talk about the cause of why that happens in the next couple of slides. So I usually picture as a rubber band that you're twisting up and twisting and twisting and coiling all around itself and getting knotted. And then if you snapped that thing and cut it open, it would fling out everywhere and release a lot of energy. That's pretty much is what's happening with solar flares and a lot of these events in the corona is you have these really twisted and knotted magnetic field lines, and then finally there'll be so much tension that they burst and they release a lot of energy. So the most common one that we look at are solar flares, just because you can see them pretty easily. Another thing that we look at that has to do with magnetic energy is a filament. A filament is called a prominence if you see it on the edge of the sun, basically. But basically, it'll look like this kind of dark line running through the surface of the sun. So it's chromospherically rooted. That just means that the base of this loop, so it's basically just a loop of plasma, the base of it is rooted in the chromosphere and extends all the way out into the corona, into the solar atmosphere. So it's relatively cool plasma, which is why it looks darker compared to everything else that we're looking at. But if you were to see a prominence, which is on the edge of the sun, it would look brighter because it's brighter than the empty space behind the sun, essentially. So that's another thing that indicates magnetic activity is a filament. And then the next thing is a sunspot. So this is a region of high magnetic activity and it inhibits convection. So convection is just a movement of mass due to really steep temperature gradients. So convection is a way, that's probably the #1 factor of how the corona gets so hot. It's still kind of a mystery as to how it gets so hot, up to 1,000,000 degrees, because convection can account for some of that, but it's still a giant temperature jump from 6,000 up to 1,000,000. But one of the things that is probably at least contributing to that is convection, where you have mass transfer that causes heat transfer, essentially. So in these sunspots, you have really, really high magnetic activity and it doesn't let that mass move. So there actually appears darker spots because once again, the plasma is cooler in a sunspot than in the rest of the sun. All right, so these are some things that we look at. I just want to quickly talk about what I looked at when I was at the CFA. So I was studying really specific type of solar flares called sigmoids. So these are just S-shaped flares. This one here is like our sigmoid poster child. It's a perfect S. There's also another one if you look kind of on the left side of the sun here, that's kind of a half S going around. So we would actually identify that as a sigmoid as well. Just a singly looped sigmoid is what that's called, because the bottom one doesn't have that perfect S shape that goes back up. But so basically what a sigmoid is, it's a twisted flux rope. So that kind of goes back to the rubber band analogy that I talked about, just a bundle of magnetic field lines. We think that they make these S shapes because of differential rotation, which we're going to talk about in the next slide. So basically all that is that the sun rotates at different speeds at different latitudes up from the solar equator. So because of these kind of curved magnetic field lines caused by differential rotation, we get these S-shaped solar flares. And the whole goal of my project that I didn't have enough time to actually get to was to kind of see if these types of flares could help predict CMEs. So a lot of times coronal mass ejections happen along with a flare of some sort. And it's been seen as we get more and more data on CMEs, even little ones, that a lot of times are associated with sigmoids or S-shaped flares. And that usually has to do with the fact that the sigmoids represent really twisted and energetic bundles of magnetic energy. So a lot of times when those burst or when those flare out, you can also have plasma coming out from a coronal mass ejection. So the end goal of my project was kind of to see whether or not we could predict CMEs using data on sigmoids from the past few solar cycles. All right. So let's talk about differential rotation now that I mentioned earlier. So basically, if you think about the Earth, it's a rigid body, right? At least once you get past the molten core. And every point on Earth makes a rotation in the same amount of time, right? So whether you're on the equator or whether you're up in Greenland, it'll take you a year to get around. And that's because the Earth is a rigid body. But when you have something like the sun, which is a hot, dense gas, mostly plasma, it's a different story because they're not bound to have the same rotation period at every point on the sun, at every latitude that you're at. So it's because of these temperature gradients and convection zones and conservation of angular momentum. It's a little complicated as to why this happens, but the basic idea is that the poles rotate slower than the equator rotates in the sun. So as we can see here, these blue lines here represent magnetic field lines. So when you have just regular straight magnetic field lines going up and down in picture A, once you move to B, as a little time has gone on, the equator moves faster than the poles. So those field lines start to bend and curve in weird ways. And as you go to picture C, you get sunspot pairs, which is basically just magnetic, like strong magnetic activity. You have southern and northern poles developing on the chromosphere and corona. And that's what causes a lot of this really turbulent, complicated magnetic activity, is that you start off with straight magnetic field lines. Eventually, due to the differential rotation, you'll have these field lines twisted up and kind of all in these complicated different arrays. So looking at these pictures, especially in B and C, you can kind of imagine how these sigmoids form because the field lines themselves kind of develop a slight S shape. So that's how these solar flares kind of make their sigmoidal S shapes as they go through. All right, and for the sun, it's about 25 days to rotate on the equator versus 34 days to rotate on the poles. So it's actually kind of a significant difference. And just as a note, the period of rotation of a star really just depends on how much angular momentum the original gas cloud, the protostar, had where it was formed. So, and that depends on how that protostar was formed, right? So if you had a giant planetary nebula event that was really energetic and spinning a lot, had a lot of angular momentum, then that gas could form a protostar that would eventually form a main sequence star that's rotating very quickly. So we have noticed in observations that a lot of other stars rotate at variable speeds. Once again, the sun is about average. So there are stars that rotate faster than the sun, there are stars that rotate slower. And all that has to do with is the original gas cloud that formed that star. All right. So what this differential rotation causes in the sun, something you might have heard about in the news recently, is the solar cycle, because we just switched into a new solar cycle about a couple weeks ago. So this is a really cool video that shows the pole reversal due to the solar cycle. So really all that it is that the poles flip every about 11 years. The solar cycle, we say, is about 11 to 11 and a half years, as far back as we've been recording them, back to the, I think, 1850s or late 1800s, they started recording solar cycles. So all that happens here is that every 11 years, as we'll see in this video, the poles switch. So you might know that on Earth we do this too, but the poles switch every about 200,000 years. So not in anyone's lifetimes or not in human lifetimes at all, really. But you probably know that the magnetic North Pole on the Earth is closer to Greenland than the geographical North Pole right now. And that's because of this 200,000 year period of magnetic pole reversal. So I'll play this video probably at least twice for you guys because it goes kind of fast. But you see we're starting in 1997. We have the negative poles in the south, positive poles in the north. And these are pretty straight magnetic field lines. They're not really twisted up yet. We don't have negative and positive overlapping. So as we go through the video, I recommend watching the dates. So we start in 1997 at a solar minimum, and then it'll flip over to its next minimum. So you'll see the negative up in the North Pole and the positive down the South Pole. And that'll happen in roughly 11 years at about 2008. And the video will end at 2013 at a relative solar minimum or maximum, sorry. And you'll kind of see there that the green and purple are all mixed up within each other. And that's how we will define a solar maximum. All right, so here, due to differential rotation, we have all these poles mixing. Now we're at a maximum. All right, and then now we're kind of settling back to minimum, but see now the negative pole is on top at around 2008. So here we're at a minimum, and now the cycle is starting itself again. So you can see these white magnetic field lines are good indicators. Yep, and now we're ending at 2013, kind of all complicated and mixed around. And that's what we define a solar maximum as. So we'll go through it one more time. So we're starting minimum. Now we're increasing to solar maximum, which is just more intense magnetic activity. Now we're settling back into another solar minimum at around 2007 or 8. And now the cycle's starting again. And you'll see them kind of overlap more and get a little more complicated. All right, so that's what's happening when we talk about the solar cycle. It basically is a back and forth of solar minimum, which is really low magnetic activity. And then due to the differential rotation, these field lines get more and more complicated. And then you get your solar maximum until they start to flip back over the other side. And then you settle into a minimum again because the field lines kind of relax. All right, so like you might have heard, it was kind of in some of the news a couple of weeks ago, we just started solar cycle 25 down here at 2020. So these are the past few solar cycles. The maxima of these, so like you see we had a peak around like 91 and then again at like 2003, and there was another peak around like 2013 was our last solar maximum. So the actual magnitudes of these peaks, sorry, the y-axis here is the number of sunspots that you get. So sunspots are often used as a tracer for magnetic activity, because remember, sunspots are regions of really high magnetic activity. So usually counting the sunspots on the solar surface at any given time will give you an estimate of how much magnetic activity is happening right now. So that's what's being counted on the y-axis here. So you'll kind of see that the maxima change as you go through different solar cycles. There have been big minima in the past, like in the late 1600s, there's what was called the Maunder minimum, where even the maximum of solar activity was barely more than the minimum, and it was way less than anything right now. So then we had like what's called a little ice age due to that, because of really, really low magnetic activity in the sun, even at the solar maxima of the cycles. And you'll also see, if anyone happens to live in Alaska or something like that, in years of higher magnetic activity on the sun, you get more intense and more frequent northern lights happening, which is kind of cool. So the best time to go see them would be probably our next solar maximum is, I think, 2023 to 2025, around there. All right. So these are some videos. This is the data that I used at Harvard when I was looking for sigmoids. So it's just comparing a solar minimum year to a solar maximum year. So you can see with the 2006 video, there are a lot less solar flares. There are a lot more dark, cooler spots of plasma. So these aren't to be confused with sunspots. It's just actually cold plasma, because it doesn't have as much electromagnetic activity happening. It's not being heated up as much. Whereas in 2013, When there's solar maximum, you have a lot more flares, a lot more total activity happening. You can see some distinct S-shaped sigmoids. One just went around there. And these videos were taken from the Hinode X-ray telescope, which is a Japanese space-based solar spacecraft. So it's really good for seeing coronal activity because it's peaks in the X-rays. Awesome. And if you see, sorry, if you notice, I should just point this out, the discrepancy in the rotation speeds, that just has to do with basically the data collection of the telescope. So they're not actually rotating at different speeds in solar minimum versus maximum. So the main thing to look at here is you have a lot more activity and a lot brighter sun in our maximum versus our minimum. All right. So one of the big mysteries that we have right now, like I was saying, is figuring out how to predict CMEs. Is kind of one of the main goals of solar research right now, because it could have such a huge like financial and just all over impact on Earth and society if that happens. So I'm just going to highlight a couple of voyages that just started. Well, one voyage and one ground-based telescope in Hawaii that are doing much more advanced solar research than we've had in the past to try and answer these questions and figure out what's happening in the corona to better understand the magnetohydrodynamic events that we have. So this first one we're going to look at is the Parker Solar Probe. I'm not sure if any of you guys heard of this, but it's a really cool one. It's called the probe that's going to touch the sky. So I can start playing this video. This light blue line is the trajectory of the probe here. So we're saying it's going to touch the sun. It'll get inside the corona of the sun, which is very exciting. The most impressive thing about the probe is its heat shield, which is really complicated to design and make. So at the apex of its trajectory, which will be in about 6 or 7 years, it'll get within 4 million miles of the solar surface, which we count that as the photosphere. To give you kind of a scale for that, the Earth is at 92 million miles. So it'll be over 20 times closer than the Earth is to the sun. So right now, actually, this is right where it's out in October. It's going outside, and then it's going to get close into the sun this coming January. And the cool thing about the spacecraft is they designed its trajectory so well. You probably notice here that it gets really close to Mercury and Venus as it goes through. So it's using Mercury and Venus's gravitational pulls to give it kind of a speed boost as it keeps going around in its trajectory. So the solar probe was launched in August 2018. It's been out a little more than 2 years, and now we're just waiting about 4 or 5 years from now for it to get close. But the data that we've already gotten from it has already answered a lot more questions about solar wind and convection zone and stuff like that in the sun. So this guy's really exciting. Hopefully there's already a lot of data to be analyzed from the solar probe, and hopefully we'll get a lot more answers about the sun as it continues to get closer to the photosphere. All right. So this is just showing its trajectory as it goes around. And then the next one that just released data earlier this year for the first time is DKIST, or the Daniel K. Inouye Solar Telescope. So this is on top of Mauna Kea, I think is how you say it. It's on top of a mountain in Maui. So a lot of telescopes are on top of Mauna Kea on the Big Island in Hawaii, but this one is in Maui because Mauna Kea is already getting super crowded. So this is the highest resolution image of the solar surface that we've ever seen. This is the photosphere, its solar surface. So each of these little grains here that you see kind of look like popcorn kernels is about the size of Texas. And the DKIST solar telescope gives us resolution of the solar surface down to about 18 miles. So each of these pixels here represents about 18 miles, which is really good for how large the sun actually is. So the actual mirror is 4 meters in diameter, which is the largest solar telescope in the world. So this is the basically best image of the solar surface that we've ever been able to get, which is super exciting. So what we're seeing here, so these bright regions where it's kind of lightish yellow and white, that's where really hot plasma is boiling to the surface down from that radiative layer underneath. All right, and then what's happening in these dark lanes here is that cooler plasma is sinking down underneath. So this kind of gives us more insight into what's happening due to convection and radiative transfer of photons right underneath the photosphere. And kind of one of the coolest things that came out of this image is you see these kind of really bright lines within the dark lanes that kind of look like gold foil. So those are actually magnetic field tracers. And they're really hot energy, even more so than the bright dots that kind of cover the kernels here. So this people think might kind of be an answer to how the corona gets so hot. So these basically trace convection as magnetic field lines kind of move up and heat up these little tiny regions up in here. So by studying these images a little more and getting some more of them of the sun, we might be able to kind of hopefully soon figure out how the corona gets so impossibly hot. All right. And that is pretty much it. So I'd be super stoked to take any questions. Yeah, thanks for having me.
Nobody's going to ask the first one. I will. You answered my first question already, which was the differential of rotation between the North Pole and the poles and the equator.
Yep.
I, for the life of me, cannot figure out why it would continue to do that. Wouldn't friction sort of slow it down?
Yeah, that's a really good question. So it has to do with the different rates of convections at different temperatures in the sun. So one cool thing that, so you know how I showed that the sunspots get you get a lot more sunspots during solar maximum, and you also get a lot more flares. A cool trend that you see in that is that you get what's actually called a butterfly diagram, which is where if you plot the latitude of flares, so if the sun, let's say, goes from here to here, if you plot the latitude of those flares over a solar cycle, at minimum, they start really like close to the equator. So basically only go up to like 10 or 20 degrees. And then as the solar cycle gets hot, like more and more magnetic as the solar cycle ramps up, the sunspots and flares extend further into higher and lower latitudes. So there's kind of a temperature gradient between the equator and the poles because of this. So you get convection happening at different rates. So that has to do with the different speeds of rotation, because to counteract these different convection rates, you still have to conserve angular momentum. So something else has to change. And essentially what that is you have faster rotation at the equator to balance that out and keep the angular momentum conserved. If that kind of makes sense. It's a complicated process. So
I guess so. We have a couple of questions in the chat.
Oh,
One
yeah.
is, how does a quiet sun affect Earth's climate?
Yeah. So that's, the thing that I mentioned about the Maunder minimum, that's actually, I gave a talk last year about, can the sun be causing climate change? And the answer is not at the level that we have right now. But yeah, a quiet sun really affects Earth's climate. So is between 1685 and 1715, I think. That's when the Maunder minimum was. So it went through about 2 or 3 solar cycles. And even when we were at the maximum of those solar cycles, that maximum was at the same level as minima in other solar cycles. So there was so little magnetic activity and so little heat being transferred into Earth's atmosphere that we had what's called the Little Ice Age. So like little towns were freezing over at like the summer and stuff like that. And basically it was a really cold 30 years, and that was caused by the quiet sun during the Maunder minimum. So what some people thought might be happening now is we're actually at a relative maximum in so right now, solar maxima over the past 30 years are higher than they've been over the past 150 years. So some people are like, oh, maybe that could be pulling climate change, but the levels of emissions can't be accounted for by the sun, basically. But So the quiet sun can actually cool the climate a ton, and a hotter sun can affect Earth's climate, but not, it doesn't affect the greenhouse emissions that are causing climate change now.
I'll have to throw in my 2 cents worth because I did write an article about the modern minimum and
Yeah.
the Little Ice Age.
Mm-hmm.
Little Ice Age started way before the modern minimum.
Okay.
It started around a couple of very large volcanic disturbances. A whole
Okay.
bunch of gunk thrown up into the atmosphere.
Yeah. I see. So that blocked the.
Yeah.
See.
It probably helped, but.
Yeah.
Now we have another question. How can the Parker probe actually enter the outer part of the sun without being destroyed from the heat?
Yeah. So that's what I was talking about. The heat shield is like, I think, one of the best pieces of engineering in modern history. So it has, I think they used a gold plated. I forgot the actual elements they used, but I don't know too much about how they made the heat shield, but it's basically just something that allows it to get within the sun when it's at its pericenter of its orbit, and it'll only be able to stay within there for like a couple of days, and then it goes way out to cool down for like the next few months, and then it swings back into the sun and gets back in there. So the heat shield allows it to go in for like maximum maybe like a couple weeks at a time before it's to get out to cool down. But I actually don't know specifically how the heat shield was made.
There's a really good article in, I think it's this month's Sky and Telescope. It tells you some of the umpteen layers of it.
Oh, awesome.
Including the carbon, I think it's aerogel middle layer.
Yeah.
We have a question, how does the solar wind move by and around Mars?
Yeah. So, I don't actually know exactly how far the solar wind extends out to. Well, no, it does go all the way through the solar system. So I think it probably does affect Mars, but since Mars doesn't have its own magnetic field, it just doesn't deflect those things. But also, I don't know if we would notice if a magnetic storm hit Mars. I mean, obviously it would be less strong than the strongest ones on Earth would be because of how much further away it is. But the solar wind does reach out to the whole solar system. So, whoops. So you can have magnetic, solar particles, plasma, and radiation hitting Mars, but I don't think it would affect it too much because it doesn't have an atmosphere. It's not deflected by any magnetosphere there, but I'm not sure that would have much of an effect on Mars because of that.
We have another question. Is there latest research on why the corona is so much hotter than the surface of the sun?
Yeah, so that's a good question. Yeah. I'm not doing solar physics anymore. I have for the past like 2.5 years, so I'm not super in with the current research right now. But the latest thing that I've heard is just about those little kind of really bright flakes within the photosphere. And those are tracers for really high convection. So just basically heat transfer up from inside the radiative layer out beyond the photosphere, because those things are reaching the surface of the photosphere, which is the thickest layer of the sun. So if we have those really thick things coming out from the core, out past the edge of the photosphere, then that could be a reason. But the last thing that I've understood from is that it's still kind of unclear how it gets to order of a million degrees Kelvin. But hopefully things from DKIST and Parker will help alleviate those in the next few years, figure some stuff out.
Question, the Earth flips its poles very infrequently relative to the sun. What determines the frequency of the flip in any given solar system body?
Yeah, so having a magnetic field at all has to do with having metal or something that produces a magnetic field within the core. So it'll pretty much only be things that have that do. I think the gas giants do the same thing. I'm pretty sure. I would have to double check on that. So I think it would have to do with how quickly it's rotating and what the structure of the core actually is. So like in things like stars, it has to do with how quickly it's rotating, because that flip is called, the flip is caused by the turbulent magnetic field lines kind of switching around. So that's what causes it for different stars. I think the flip in planets and gas giants and things like that would have to do with the composition of the core, and probably have to do with this rate of rotation as well.
Let's see. I have a question again. When we flip, it could be happening soon because the pole is changing directions
Yeah.
quickly. What's going to happen if we get hit with a CME?
That's a really good question. Yeah, so I think we would still have a magnetosphere. It would just be flipped around and the field lines would be going the opposite direction. But I think, yeah, the biggest concern would be kind of the transition period between when we're actually flipping poles and what happens to our magnetic field then, and will we be as well shielded. So I think there could be a good argument that it would be, CMEs would be more dangerous. We wouldn't have as much deflection while it's actually flipping the poles than if we have a stable magnetic field where it goes from north to south and it's not in the middle of a flip. So yeah, I think CMEs would be more dangerous then.
Anyone else? Any questions?
Steve, can I ask a question verbally?
Certainly.
Patty, I'm a ham radio operator. So are at least a couple of other people in
Oh, awesome.
astronomy club. Good HF radio transmissions are associated with solar maximums, or with the maximums in the solar cycle.
Okay.
We've been told that's because there are more sunspots during that period.
Right.
Our transmissions bounce off of the ionosphere, and so what is the relationship between the solar maximum and the ionosphere being a good thing for radio transmissions to bounce off of?
Yeah. So in a solar maximum, you have more sunspots and you have more flares because they're both caused by the higher magnetic activity. And when you have more flares, those things are emitting photons out through the solar wind. And when those get inside of our magnetosphere, those photons ionize gas in the ionosphere, in the Earth's atmosphere. So if you have more hard ionization of gases there, I'm assuming that's what would help it bounce off better during solar maximum, because you have more ionizing radiation coming from the sun because of flares and more outflows from the solar wind. So that'll ionize the ionosphere even more during solar maximum than during minimum. So I think that would be it.
That's great. So it's not really the sunspots, but sunspots are an indication of more solar flares that
Yeah.
create ionization in our upper atmosphere.
Yeah. So they're all related. Like the baseline that glues them all together is higher magnetic activity. And higher magnetic activity leads to more sunspots, which are just regions of thick, dense magnetic fields, and more flares, which are electromagnetic radiation being burst out. So those two are correlated to each other in that they're both caused by higher magnetic activity, which occurs during solar maximum. So if you have more sunspots, that's not what causes more solar flares, but they're both caused by the same events.
Thank you very much.
Other questions? Feel free to unmute and ask them.
Steve, I have a question.
Go for it.
Thank you, Patty. That was a great talk. Do we understand, I guess, quantitatively in a formula when we would expect magnetic field lines to break or snap? And I mean, is this a thing that can be studied on the Earth in the lab?
Yeah, that's a super good question. So that is part of the thesis that I did in my undergrad. So with those sigmoids, I basically cataloged all of them and their properties over the last solar cycle, but I also did some modeling of them. So the way that we modeled them is called the flux rope insertion method. So I talked about flux ropes a little bit. It's just basically like a thick rope, a bundle of magnetic field lines, and they get all twisted up. And then there's, depending on how big they are, there's some tension and energy that they can't be maintained under, and that will cause the flip. So the thing that we can do on Earth to look at it is called MHDs. They're magnetohydrodynamic simulations. Yeah, magnetohydrodynamic is the MHD. So MHD simulations is what's being done in labs to kind of look at this, because there's nothing similar that occurs naturally on Earth. So basically what this is, you take a really hot, dense plasma and get it to as high temperatures and density as you can, and you put it under magnetic fields and kind of see what happens as you vary the magnetic fields. So that's how we get these baselines for like at what force or at what tension do these things erupt? Do these magnetic field lines, can they no longer continue to keep twisting, and will they just erupt and flare? So from these MHDs, we're kind of trying to understand what's happening in the corona a little better, but we still are kind of limited by what can happen in the lab, but it gives us a good baseline that we can then put it into modeling simulations that model the sun on a computer, and that gives us like a rough order of magnitude for what force can these things be under before they will erupt. So that's kind of where we're at with that. We try to model it and use lab predictions to put in our estimates of values.
Great, thank you.
Mm-hmm.
Any questions? Not seeing any in the chat. If there are no other questions, Patty, I thank you very much for your very interesting talk.
Yeah, no problem. Here, I can stop sharing.
We will call it. Everyone have a good evening.
Great. Yeah, thank you for having me.
Oh, you're very welcome.
I have one last question. I'm sorry.
Yeah.
Was this inappropriate? I assume the meeting was concluded. There was a blue, sort of a blue thing. Was that from the sodium layer? Something about a blue, you know, I've even forgotten the context now, but something blue in the sky. Was that from the sodium layer of our atmosphere, or was that something from the sun?
Wait, you mean like recently, like in?
Something from your talk.
Oh. When I talk about blue.
I'm not trying to,
Let me look back at it. Oh, was it from the Aurora Borealis?
Yeah. That's what it was. Right. Thank you.
Yeah, exactly. So basically, when something is ionized, you have electrons jumping around to different energy bands within the atom, and it has a characteristic wavelength associated with it because these bands are quantized. So if you have something that is like a photon comes in, gives it energy, it can jump from one band up to the next. You get an absorption feature, which is, so if it jumps up from there, and then where you get the photon from that we see in the northern lights is it relaxes back down to its original state, and it re-emits that photon back out, and you have that energy gap. And because those photons are always going at the speed of light, depending on the energy gap, you have a characteristic wavelength associated with it. And usually with the northern lights, because of exactly like you said, the sodium in the atmosphere and the different elements that we have in the upper atmosphere, the different kinds of atoms that are ionized, the characteristic wavelengths that are emitted are usually green and blue light, which is why the northern lights are green and blue.
So it's the sodium, or is it something else too?
I think it's sodium, but I'm not 100% sure.
No problem. Thank you so much for a wonderful talk.
Thank you.
Thank you.
Yeah,
Very,
problem.
very interesting, fascinating.
Awesome. Thank you.
Anybody else? Last chance. Going once. Thank you very much. Everyone have a good
right.
evening.
Good night. Bye bye.
Night.
Good night.
Thanks again.
Night.